Welcome to Lecture 4.5, Phase Portraits with Real Eigenvalues. Okay, so we saw an example of this last time. We had a homogeneous system, x prime equals ax, up here. And the big idea of last time was that pretty much everything is determined by the eigenvalues and the eigenvectors of A. So in this case, we had two negative eigenvalues, this, and here are the two corresponding eigenvectors. So once we have that, we have the general solution right away. It's C1 e to the lambda 1t times the first eigenvector plus C2 e to the lambda 2t times the second eigenvector. And also what we did is we plotted these solutions, what was called the phase portrait. And that's what the topic of this lecture will be on. So the phase portrait, remember, is y2 minus y1, and how we did that is we first plotted these two eigenvectors. So v1 is 1, negative 2. Let me use my pen now. So this is v1. Let's plot that. It's supposed to go to the origin. And then v2 is 3, 2. So that's going to be, this is 2, say this is 1, and then 3, 2 is going to be maybe, let's say that's 3. So 3, 2 is going to be up here. So what I've done is I've plotted this actually let me do that in black. I'll do that in red so you can actually see it when we start drawing other things on top. So there's v1 and there's v2. And then from here, we drew lines through these eigenvectors. So I call these are the eigenvector lines. Everything on here is actually an eigenvector. And then because the eigenvalues are negative, I drew inward arrows on each of these. So solutions that begin on one of these lines at t equals 0 dive in toward the origin. However, solutions along this line dive in faster because this exponential function goes to 0 quicker than this one does. So I think last time I drew multiple arrows on here just to signify that this is dives in faster than this. So I think of this as like a hill, as I said last time. So think of this as a bowl, and this is the bottom of the bowl. And if you go along this way, you're walking downhill, but not very steep. But if you're walking along this direction or this direction, it's also downhill, but it's very steep. So can you picture that? So it's not very steep in this direction, and it's very steep in this direction. So then I said, well, okay, so what if you start here? You take a ball on this hill and you drop it here. What's going to happen? Well, just intuitively, it's going to fall in the steepest direction more than first, so it's going to bend in this direction, something like this. And similarly, these curves are all going to bend. So here it's going to bend in that direction. And just use your physical intuition about like a ball. If you could picture this hill, then you could picture how a ball is going to fall or roll down it. Okay, so that was the big idea of last time. And what we're going to do now is we're going to look at similar systems where we have two positive where we have distinct real eigenvalues. So we'll look at the case when we have one positive and one negative, and when we have two positive ones. So here's one. Here's a homogeneous system. This is, I'll call this negative, let's see, get my pen back. So this is not negative, sorry, x prime equals a times x. And you may remember that when we learned about eigenvalues and eigenvectors, I think this was one of the matrices that we actually used as an example. So we've computed the eigenvalues and eigenvectors of this matrix before. And if you recall, they are these things right here. So we have one positive and one negative. Regardless, because we have two eigenvalues and two eigenvectors, we have the general solution. It's c1 e to the 3t times the first eigenvector plus c2 e to the lambda 2t times second eigenvector. So let's plot the phase portrait. So as before, we're going to have, so it's going to be y2 minus y1. Okay. So let's plot these vectors. So v1 is going to be 1, 2. That's going to be, so this is v1, this is 1, this is 2. And then v2, let's make that a little darker because we're going to go over it. And then v2 is 1, negative 2, so that's going to be something like this. So to draw the face portrait, let's extend these eigenvector lines. Like this. And now let me just note that along this line, the eigenvector is lambda equals -1, and along this one it's lambda equals 3. Let me actually write lambda 1, lambda 2, though that doesn't really matter. In fact, I can do that better. So this is lambda 2 equals -1. Okay, so curves that start on this line are going to dive toward the origin because the eigenvalue is -1. Remember that? So the limit as t goes to infinity of I guess this is y2 of t is, remember, so I'm going to call y2, so this is going to be y2 of t, and this is going to be my y1 of t. So as t goes to infinity, taking the limit of y2 of t, that's e to the negative t, 1, -2, I just get the vector 0, 0, because this thing goes to 0. So that means anything along here is going to dive in toward the origin. So I'm going to denote that with arrows. And then conversely, anything along here, let's compute this limit. Take the limit as t goes to infinity of y1 of t. So this is the limit as t goes to infinity of e to the 3t, 1, 2. And well, technically that limit doesn't exist. So let me modify this a little bit. Let me say the limit in the norm of that. So that's the distance from the origin. If I say this, now I can safely say that that is infinity. So in other words, curves that start here go that direction. They go away from the origin. So we have something like this. And this is actually probably the easiest case that we'll see in this lecture because you don't have to worry about the relative bend in one direction versus the other. Any curve in here is going to sort of swing that way. This is called a saddle point. So let me fill in the curves like I did before. So there's I should mention that these curves approach these lines pretty quickly. And so it's tempting to actually draw a curve like this. Now there is a curve that goes through here, but so this curve is going to every curve is going to approach in the limit backwards this line, this direction, and in the other limit it's going to approach this one. Because if you think about it, as t gets very negative, let's start with when t gets very positive. When t gets very positive, this thing dominates, and you can pretty much ignore this term. So for large, actually not that large values of t, when t is just, t doesn't have to be that large to make this term negligible, and then your solution is almost on this line. It's in this direction. So for moderate to large values of t, we're almost on this line, and conversely, if for small values of t, for negative, so if t equals -2, -3, -4, this term is negligible and this term dominates, so we're over here. So let me fill in these lines, and it's going to look like this. And again, remember, every single point here is going to have a solution that goes through it. So this point here is going to have a solution curve that goes through it, but it's probably going to look something like like that. Okay, so this is called a saddle point. Saddle point. And I think that's probably all I need to say about this case. Okay, so let's do the third case. This is when we have two eigenvalues that are both positive. Here, I'm not even going to give you the matrix. I'm going to say, let's just suppose we have a system, x prime equals ax, and we know that the eigenvalues and eigenvectors are these things right here. So let's do this. First thing to do is just acknowledge that we know the general solution. Again, it's C1. Oh, I didn't realize I had my pen out. It's C1 e to the lambda 1 t times the first eigenvector plus C2 e to the lambda 2 t times the second eigenvector. So let's plot what this looks like. So I'm going to draw the eigenvectors, 1 positive 2, something like this, and 1 negative 2 is going to look something like this. Then I'm going to draw the eigenvector lines. And let me note that this one is when we have lambda 1 equals, actually that's lambda 2 equals 5, and this is for lambda 1, which happens to equal 1. So for both of these things, so let me just do the first one, the limit as t goes to infinity of y1 of t is the limit as t goes to infinity of, well, let me take the absolute value of e to the t times 1, 2, and that's going to blow up, that's going to become infinite. And similarly, the same thing for y2 of t is just, this is going to be e to the 5t. So both of these things are curves on here are going to be going away from the origin, but this one, e to the 5t blows up faster than e to the t blows up. So I'm going to draw more arrows along here just to signify that this is going to dominate faster than this one. Okay, so let's think about what happens if your curve starts something like, say, in the middle, something like this. Okay, so here's one way I like to think of it. Personally, I don't use the hill analogy as much here, although I guess you could think of this as maybe the top of a hill. But I like to start off here, and then as t gets larger and larger and larger, this term is going to dominate, and this one's going to be negligible because e to the 5t grows a lot faster than e to the t. That means in the limit, my curves are going to be in this direction along this eigenvector rather than along this eigenvector. So this is the dominant direction. So as time goes to infinity, this is going to approach, it's going to get more and more parallel to this direction. So curves are going to come in from here and then they're going to bend that way. If they were to bend the other way, that would mean that they would, in the limit, be approaching that direction, and that's not the case. So curves are going to be, so let me draw this in the limit, they are going to, so they will be bending in this direction. So something like, oh, that's a bad example, that's supposed to go in toward the origin. Maybe I can redo that. Something like this, and then my curves are going to be bending in this direction, and similarly like that. Okay, so notice that if I were to swap swap the signs of these, if I were to make this -1 and make this -5, then the face portrait would be exactly the same. I should label my axes, except the arrows would be reversed. And if this one is -5, then this one is going to go to 0 a lot quicker than the other one. So I would draw more arrows on this line than this one. They would just be pointing in, and then my ball that starts here is going to fall this direction faster, so it's going to bend in that direction. So again, I use different methods for when the eigenvalues are positive or they're negative. When they're negative, I like to think of this as a bowl, and when they're positive, I think of the dominant direction as being where the curves are the direction of the curves in the limit. Although you can do either, if you don't like one of those, like if you don't like the bowl example, you can just make your eigenvalues positive, use this method, and then just switch the direction of the arrows, whatever works for you. Okay, so let's summarize what we've learned so far. So first of all, I'm going to start using the variables x instead of the variables y. Recall that we used y because we started with an inhomogeneous system and we changed variables to make it homogeneous. But from now on, I think let's just go back to using x because I think it's easier. It's more natural. So if we have a system, x prime equals ax, then A has distinct real eigenvalues, lambda 1 and lambda 2, and corresponding eigenvectors, which must be distinct because they could scale by different amounts, then the general solution to this system is this thing here. And in fact, this isn't just restricted to these things being real. So if these are complex, we get the same thing, but we will do some extra work to turn them into sines and cosines, like what we did for second order equations. And that's the topic of the next lecture. But for now, let's just assume these are real. This is a general solution. And then we can draw the phase portrait. And the phase portrait allows us to visualize every single one of these solutions. And there's a whole 2-parameter family of them. So for the phase portrait, that's going to be x2 minus x1. Let me sketch x2 and x1. So the first thing to do is we draw the eigenvector lines. So we draw the eigenvector. Suppose this is v1 and suppose this is v2. Then we draw the whole line that goes on top, all scalar. So this is supposed to be straight. Maybe I can fix that a little bit. Okay. So this is, and let me draw this v2 and redraw this so you can see it. So this line consists of eigenvectors with eigenvalue lambda 1, and this line consists of eigenvectors with eigenvalue lambda 2. Okay, so if these things are both, or let's just fix one of these, like lambda 1, curves that start on this line will continue on this line forever, and they're either going to dive toward the origin or they're going to move away from the origin. If lambda is positive, then the solutions move away from the origin because this limit, which is one of these terms up here, is infinite because this exponential blows up. However, if the eigenvalue is negative, then the solutions move toward the origin because this exponential goes to 0. And finally, the solution curves off these lines. So if we have a solution curve through this point, then it's going to either go toward the origin or away from the origin. But it's going to bend. It's either going to bend this direction or that direction, and that all depends on the relative difference in lambda 1 and lambda 2, more so than the actual. So think of it like as the ratio. So if lambda 1 and lambda 2 are both, suppose these are both positive but small, like 0.01 and 0.05, then solution curves are going to move away from the origin, but they're going to do so slowly because these exponentials are blowing up slowly. In that case, it's going to go in this direction. However, if these are, instead of being 0.01 and 0.5, if this is 1 million and 5 million, then the curves are going to move away from the origin very rapidly. So instead of like a turtle, it's going to be like a race car like that, but they're still going to have the same bend because the ratio, the relative size of lambda 2 and lambda 1 are the same to the other case when we had 0.05 and 0.01. So what I'm going to finish with is I'm going to give you 2 examples of phase portraits with and I'm going to slightly change the eigenvalues, and I want to talk about how that changes the phase portraits. So let me suppose that we have this the same eigenvectors. So I'm going to try to draw these to be the same. Let's see how well I do. So this is going to be lambda 1, 2, and this is, say, this is the first eigenvector, and this is the second eigenvector. I don't need to draw v1 and v2. Okay, so let's suppose now that lambda 1 is 10, and lambda 2, let's put this up to 11. And then on this phase portrait, let's suppose lambda 1 is 1 and lambda 2 is, say, it's also 11. Okay, so let's think about what the relative bend and the curves off these lines look like. Actually, before I do that, let me mention that, let me put these arrows in this direction to mention that, or to, I guess to denote that these curves are going to be moving away from the origin. And now 11 is a lot bigger than 1, so I'm going to put a lot of these little, this is just for my own reference, put a lot of these marks over here. And 11, yeah, 11 is a little bit bigger than 10, so maybe not much. Let me put in one extra mark over here. Okay, so a curve over here, it's going to go toward the origin, but it's going to bend massively in this direction. And the way I like to think of this is because as time goes to infinity, this direction dominates over this direction. Think of it like wind, this, or gravitational force. That's a good way to think of it. This pull is stronger than this pull. So as time goes on, the curves are all going to bend that way. And they're going to bend this way very quickly because e to the 11t grows faster than e to the 1t. So curves are going to look like this, maybe. They're going to have a big bend to them. Have a big bend. I'm sorry, oh, that arrow's the wrong way. And so something like this. Part of my curves are supposed to be diving into zero. They're not doing a very good job of it, but these things should eventually go into zero. And then the other here, it's going to be something like this. It's going to have a lot of bend. And now let's compare it to this one. So it's going to bend in this direction. In the limit, this direction is going to dominate this one. Absolutely, because e to the 11t grows faster than e to the 10t, but it's going to do so, it's going to be a lot more gradual. So a curve here is going to maybe go slightly bend in that direction. Maybe something like this. So yes, it will bend, but not very much. Maybe just a slight bend here. And over here, so let me shoot a curve that goes off halfway in between here and here. And it will bend eventually in that direction. Something like this, like this. So qualitatively, you can see the difference. And now let's take it one further. Let's suppose I had made this 10.99999 and this being 11. Picture what's going to happen. Well, then these things are going to go off. It's going to basically look like a star. And so turns out, we will see later, that when we have a repeated eigenvector and repeated eigenvalue and two eigenvectors, yes, these things will actually be going off into straight lines. It will look like a star. And let me ask you one more thing now. Let's suppose instead of this being 11 and this being 1, suppose this was 11, this was 0.0001. What would that look like? And these things would be going, these things would be almost straight lines. And the very end they would bend. Because when t is very, very negative, that's when e to the 0.01 becomes, dominates over this. So just sort of as a preview, let me finish by asking you, what if, so these are distinct real, and actually I'm assuming these are non-zero, but what if these were zero? Let's suppose I had we'll talk about this more later, but let's suppose I had a lambda 1 equals 0, and let's suppose that this was lambda 2 equals 11, say again. So what are the curves going to look like? Well, what's the general solution going to look like? In that case, the general solution, let's do the same thing. It's going to be x of t equals c1. What's e to the 0? That's 1. So c1 times v1, which is 1, 2. I'm assuming that's what this vector is. 1. Oh, no, that's more like 2, 1, right? So yeah, let's change that to make that a 1, make that a 2. 2, 1 plus c2e to the 11t times negative 2, 1. So in that case, the general solution, this is actually not an exponential. And these curves are, instead of bending, they're going to bend and never actually go that way. So the curves are going to look like, they're going to go out in that direction, and they're going to go out in that direction, and they're never going to actually bend back into the origin. Last question, what is the steady state solution to this system? Well, you may say it was 0, 0, right? 0, 0 is always a steady state solution. But in this case, there's actually more. Notice that if we start anywhere on this line, our curve is not going to move. So if we drop the ball right here, and as time gets larger, it's stuck. It stays right here. So this entire line consists of steady state solutions. And think about how that makes sense with this. This entire line consists of the points when C2, the functions when C2 is 0. So when C2 is 0, we can cross that out, and there is our solution. And here we have a whole one parameter family of solutions, one for each value of C1 algebraically, and then geometrically or graphically that corresponds to all the solutions where we just get stuck, which is any point on this line.